It was March 15th, 1944, 09:30 hours, in a heavily guarded facility outside Moscow. The compound's industrial buildings cast long shadows across the frozen tarmac as Major Ivan Petrovich Kozlov stepped out of the black automobile, his breath visible in the bitter cold. Petrovich was 47 years old, a senior aviation engineer with the USSR's Technical Directorate, and he had spent 20 years reverse engineering captured enemy aircraft. Today, however, would be different. Very different. The news had arrived 3 hours earlier. An intact American P-51 Mustang had crash-landed near Poltava, Ukraine, during a stray bombing run. The pilot had ejected. The aircraft was captured by Soviet forces with minimal damage to its critical systems. What this meant was unprecedented. A direct window into American industrial capacity, American design philosophy, and American aeronautical engineering. As Petrovich walked through the heavy steel doors of Hangar 7, his security escort flanking both sides, he didn't yet know that this single captured fighter would challenge every assumption he'd been trained to hold about Soviet technological superiority. The propaganda ministry had spent the last 3 years assuring him that Soviet aircraft design was not merely competitive, it was advanced. It was modern. It was proven in combat. What waited inside that hangar would establish, with brutal mathematical certainty, that everything he'd been told was a comfortable lie. The P-51 stood in the center of the hangar under bright work lights, its plexiglass canopy gleaming, its aluminum skin unmarked except where the landing gear had buckled on impact. It looked, from a distance, almost fragile compared to Soviet fighters. Petrovich had examined enemy aircraft before. He knew the general dimensions, the rough performance figures, the recognized tactical advantages. But he had never seen an American fighter that looked quite so economical in its construction, so refined. His assistant, Lieutenant Dmitry Volkov, stood waiting beside a workbench laden with technical instruments. The younger man's face held the particular kind of tension that comes from knowing your superior is about to face an uncomfortable truth. "The engines are intact," Volkov said carefully. "Both of them." "Both engines are intact on a single-engine fighter?" Petrovich asked, the absurdity momentarily confusing his mind. "No, sir. One main engine. The second engine in the fuselage. It's not a second engine, it's something else. We're not sure what it is exactly. We thought you should examine it first." Petrovich approached the captured aircraft. The moment he looked inside the engine compartment, he understood why Volkov's voice had carried that particular tension. Before he had even begun his systematic technical examination, something fundamental was already challenging his training. The engineering density was remarkable. The precision was American, meaning it was intentional, which meant it was systemic, which meant it was backed by industrial capacity. What he discovered over the next 40 hours would reshape his understanding of not just aircraft design, but of global military reality itself. Petrovich began with the obvious component, the Packard FIPA 1650-7 engine itself. The American designation was stamped on the engine block. As he removed access panels and began his preliminary examination, his trained eye moved across the architecture with methodical precision. The displacement was 1,649 cubic inches, 27 liters. That was standard. Soviet designers knew these numbers, but the configuration held surprises. The engine produced 1,620 horsepower at sea level with military manifold pressure, and 1,695 horsepower at 20,000 feet with war emergency boost. The numbers themselves weren't shocking. Soviet engines could produce similar power, but the consistency was extraordinary. "Look at the fuel injection system," Petrovich said, more to himself than to Volkov. "It's mechanical. Individual fuel injectors per cylinder. 12 cylinders, 12 independent injectors. The calibration tolerance on these injectors, measure them." Volkov used precision calipers on 3 randomly selected injectors. The measurements were 44.73 millimeters, 44.71 millimeters, 44.74 millimeters. Variation, 0.03 millimeters. Petrovich ran the calculation immediately. Less than 0.007% tolerance variance. "That's not possible," Volkov said quietly. "Manufacturing something to that tolerance in mass production would require—" "It requires machine tools we don't have," Petrovich finished. He moved to the supercharger assembly. The two-stage, two-speed supercharger represented significant engineering complexity. The intercooler, the component that cooled the compressed air before it entered the cylinders, was machined aluminum with precision cooling fins. He counted them. 47 fins per square inch. The pressure casting was flawless. No air bubbles, no imperfections. "What is this material?" he asked, running his fingers across the casting. "We're having it analyzed, but preliminary assessment suggests a high-grade aluminum alloy, possibly aluminum-copper-magnesium." Petrovich examined the main fuel system. The pump capacity was rated at 68 gallons per hour under normal operation, with a backup system providing 34 gallons per hour. Dual pumps, redundancy built into a fighter aircraft. He pulled fuel line specifications from a notebook. American fuel lines were manufactured to SAE 1018 seamless steel tubing standards, with working pressure of 450 pounds per square inch. "The fuel system has redundancy," Petrovich said, the realization settling on him like weight. "And this fuel pressure, 450 psi, that's 35 kilograms per square centimeter. That's significantly higher than our systems." He moved to the electrical system. The generator produced 30 kilowatts of electrical power. The battery system was 24-volt, two separate battery banks for redundancy again. The wiring harness was bundled with precision, each wire labeled with hand-stamped designations. He traced the main power distribution. Every circuit had a dedicated breaker. He counted 17 separate breaker types, each one a different amperage rating for different systems. "Why would they install redundant systems in a fighter aircraft?" Volkov asked. "That adds weight, complexity, maintenance requirements." Petrovich didn't answer immediately. He was moving toward the manifold assembly, the structure that connected the cylinders to the supercharger and engine. The manifold was cast iron, but the casting quality was exceptional. He examined the internal geometry. The valve timing mechanism was precision ground. He requested the clearance measurements. After examination, the valve overlap was 42 degrees, with precisely controlled timing. The lift specifications were 0.371 inches at maximum, with a valve spring pressure calibrated to 280 pounds. He compared these against Soviet specifications in his notebook. The American design was operating closer to maximum thermal and mechanical stress points than comparable Soviet engines. This was not conservative engineering. This was optimized engineering. "These aren't prototype tolerances," Petrovich said finally. "These are production tolerances, which means they're mass-producing engines to specifications that would require months of hand calibration if we attempted them, and they're doing it at scale." He stepped back from the engine. His initial reaction had been curiosity. Now something deeper was forming, a recognition that what he was examining wasn't a generational advantage. It was a systematic advantage, and that suggested something far more disturbing than technical superiority. It suggested industrial capacity so vast that it could maintain superiority even while producing in volume. The fuel system demanded deeper analysis. Petrovich moved to the main fuel tanks, which were housed in the wings rather than the fuselage. The tanks were self-sealing, a rubber-coated internal bladder that would automatically close puncture wounds to prevent fuel leakage after combat damage. The thickness of the rubber compound was 6.2 millimeters, applied with flawless uniformity across 2,800 square inches of internal tank surface. "How many aircraft is this design applied to?" Petrovich asked. "All American fighter aircraft, according to intelligence reports," Volkov answered. "Every Mustang, every Thunderbolt, every Corsair, standard installation." Self-sealing tanks represented a deliberate choice to prioritize pilot survival over structural weight economy. Petrovich knew from intelligence that German fighters had rejected this approach. The additional weight was deemed unacceptable. The Americans apparently had decided otherwise. He moved to the hydraulic system. The main hydraulic pump produced 1,200 psi, 82 kilograms per square centimeter, a pressure specification that would require stronger cylinders, more durable seals, and more sophisticated manufacturing. The system included 3 independent hydraulic circuits, one for landing gear, one for flaps, one for flight control surfaces. Redundancy again. "This is the 3rd time I've found redundant systems," Petrovich said, moving now to the cooling system. "The engine has a main radiator and an auxiliary cooling system. The hydraulics have 3 separate circuits instead of one unified system. The electrical system has 2 battery banks. Every critical system is designed to survive partial failure. The cooling system used glycol as the coolant medium, circulating through the radiator at approximately 2,000 liters per hour. The radiator assembly itself was a marvel of precision manufacturing. Hundreds of thin aluminum tubes brazed together in a precise geometry. The design allowed the engine to maintain 90 degrees Celsius internal operating temperature even during high-altitude flight, where external temperatures dropped to -30 degrees Celsius. "They're designing for survivability," Volkov suggested carefully. "They're designing for logistics," Petrovich corrected. "These systems presume damage. They presume imperfect conditions. They presume that pilots will survive long enough to fly multiple missions, which means they're designing for sustained combat. Industrial-scale combat." He turned his attention to the aircraft frame structure. The fuselage was semi-monocoque aluminum construction, the same design approach Soviet engineers used. But the aluminum alloy appeared to be 24ST aluminum copper, a composition known for high strength and fatigue resistance. He requested stress analysis on several airframe components. The results were systematic. The fuselage was designed to withstand 15 Gs of loading in extreme maneuvers. The wing attachments were over-engineered by 40% compared to the theoretical minimum. The landing gear shock struts were designed to absorb impacts at 3.2 meters per second, significantly higher than most aircraft. "This is not minimalist design," Petrovich said. "Every component is built for repeated punishment. The landing gear is designed for hard landings, because they're expecting pilots to make hard landings repeatedly. The wings can withstand extreme maneuvering, because they're expecting pilots to push the aircraft to its absolute limits, consistently." He moved to the propeller assembly, the Aero Products constant speed propeller with automatic pitch control. The system used oil pressure modulation to continuously adjust blade angle between 13 and 56 degrees. The response time was controlled to prevent overhunting and vibration. "The propeller synchronizes pitch to engine demand automatically," Petrovich said. "That's not just engineering sophistication. That's engineering assuming the pilot will be in combat long enough to benefit from automatic optimization. They're designing for sustained engagement." The air intake system was equipped with a carburetor air filter of remarkable sophistication, a replaceable element with 400 square inches of filtering surface. The pressure differential gauge indicated when maintenance was required, preventing pilot confusion about engine health. "Even the maintenance systems are designed for pilot convenience," Volkov observed. Petrovich was moving through the aircraft now, cataloging systems faster. The radio installation occupied a specific compartment with cooling ducting, indicating electronic components sensitive to temperature fluctuation. The gun sight was a Norden computing gun sight, a precision optical instrument with mechanical calculation built in. The instruments panel held 17 separate analog gauges, each one readable in sunlight, each one independently mounted to prevent vibration cascade. "There's no economy here," Petrovich said finally. "Not in the design sense. There's sophistication. There's redundancy. There's engineering that assumes high utilization rates and extended operational life. And there's precision manufacturing throughout, not in isolated components, throughout." He sat down on a workbench and looked at the captured aircraft with new recognition. "This isn't advanced. This is different. This is the product of a different industrial philosophy. Before we continue with what Petrovich discovered next, I want to hear from you. What's the most surprising WWII technology you've learned about? Drop a comment below and let me know where you're watching from. And if you're finding this technical analysis fascinating, hit that like button. It helps more history enthusiasts discover these stories. By hour 8, Petrovich had isolated the component that would occupy the next 12 hours of technical examination and would fundamentally reshape his understanding of American industrial power. The component was the two-stage supercharger's intercooler, Soviet engineers had attempted intercooler design since 1941. The technical challenge was substantial. Compressed air, reaching 150 degrees Celsius, needed to be cooled to operational temperatures without sacrificing pressure or flow rate. The thermodynamic requirements were clear. The manufacturing reality had proven impossibly difficult. The intercooler required precision aluminum casting to specifications that Soviet manufacturing couldn't consistently achieve. The internal cooling fins demanded 47 individual fins per square inch, each one exactly 0.81 millimeters thick, each one parallel to within 0.15 millimeters. The brazing process that joined the fins to the cooling tubes required heating the entire assembly to 580 degrees Celsius without warping the geometry. Petrovich had reviewed 3 separate failed Soviet intercooler programs. The first, in 1942, had attempted to manufacture intercoolers using identical design principles. The fin geometry proved impossible to maintain during the brazing cycle. The components would warp, the fins would bow, the pressure drop across the intercooler would exceed acceptable limits. The second attempt in 1943 had used a different approach. Thicker fins, fewer of them, larger internal passages. This avoided the manufacturing complexity, but sacrificed cooling efficiency by 31%. The engine's performance dropped proportionally. The third attempt had been abandoned entirely. Soviet engineers determined that intercooler development would require entirely new machine tools, precision casting facilities, and probably 2 to 3 years of development time. The resource allocation was deemed unaffordable. "This intercooler," Petrovich said, holding the component under the work lights, "represents something we attempted 3 times and abandoned 3 times, and the Americans mass-produced it." He rotated the component. The internal fin geometry was flawless. He used calipers to measure fin thickness on 12 randomly selected fins. The measurements 0.81, 0.80, 0.82, 0.81, 0.80, 0.81, 0.81, 0.82, 0.80, 0.81, 0.81, 0.80 millimeters. The variance was 0.02 millimeters maximum, less than 2.5% tolerance variation. "How is this possible?" Volkov asked. "Precision machine tools," Petrovich said, "thousands of them. Tolerances controlled to 0.01 millimeters. Probably automated production lines where consistency is maintained by mechanical precision rather than operator skill." He moved to the turbo supercharger housing. The housing was ductile iron, cast to specifications that included internal cooling passages. He requested sectioning, cutting the component in half to examine the internal passages. What the sectioning revealed was extraordinary. The internal passages were precision cast, not hand-drilled. The diameter was 8.74 millimeters throughout a 47 centimeter passage path. The tolerance was maintained through the casting itself, not through subsequent machining. "They're casting precision directly into the component," Petrovich said. "They're not casting oversized and then machining to tolerance. They're casting to final tolerance directly." This represented a different manufacturing philosophy entirely. Soviet manufacturing typically overcast and then machined. The American approach eliminated the machining step entirely, suggesting either extraordinarily precise mold making or automated casting processes that could maintain tolerance consistently. The supercharger rotor assembly revealed the same pattern. The rotor was a precision aluminum alloy casting, containing internal cooling passages cast directly into the rotor structure. The rotor shaft tolerance was held to 0.05 millimeters, a specification that required either hand lapping or precision grinding on every single rotor manufactured. "They're manufacturing each of these components to essentially prototype tolerances," Petrovich said quietly, "but they're doing it in series production." He calculated the implications. Each P-51 Mustang engine contained approximately 1,247 components of various precision classifications. If even 40% of those components required tolerances below 0.1 millimeters, and preliminary examination suggested the percentage was much higher, then each engine represented several hundred hours of manufacturing attention. "How many of these engines do you estimate they produce monthly?" Petrovich asked. Volkov consulted intelligence documents. Minimum 2,400 engines per month. Maximum estimates reach 3,200. So they're producing between 2,400 and 3,200 precision-manufactured, multi-system engines every single month. Each one manufactured to tolerances that would require hand calibration if we attempted them. Petrovich sat down heavily. "They're not ahead of us in aircraft design. They're ahead in production capacity. They're ahead in machine tools. They're ahead in the ability to maintain precision at industrial scale. And that advantage is not something you close. That's something you surrender to." The technical examination was one thing. The production data was something else entirely. Petrovich spent the next 4 hours requesting every intelligence report, every intercepted transmission, every production estimate that Soviet intelligence possessed regarding American aircraft manufacturing. By 15:30 on March 16th, he had assembled a comprehensive picture that moved beyond technical analysis into something resembling arithmetic calculation of national power. The Soviet Union produced approximately 2,200 fighter aircraft per month during 1944. This was full production capacity, the absolute maximum that existing factories, raw materials allocation, and labor could sustain. The figure was classified, compartmentalized, and considered a state secret. According to intelligence reports, the United States produced 4,680 fighter aircraft per month during the same period. That figure alone required no interpretation. It was a ratio of 2.11. The Americans were producing more than twice the fighter aircraft per month than the Soviet Union, despite fighting the Japanese and maintaining reserves. But the fighter production was only the beginning. The American bombers. The United States produced 1,140 heavy bombers per month, B-17s and B-24s. Soviet bomber production was 340 per month, another ratio approaching 4.1 in American favor. "That's not possible," Volkov said, reading the figures. "That would require entire industrial regions dedicated to aircraft manufacturing." "Continue reading," Petrovich said quietly. "The engine production. Approximately 800 to 900 aircraft engines per month from the United States. Soviet engine production, 2,100 per month. Ratio, 4.2.1. The aluminum production, the United States produced 143,000 tons per month. The Soviet Union produced 11,000 tons per month. Ratio, 13.1. "That's not an industrial advantage," Petrovich said. "That's an industrial chasm." He requested steel production figures. The United States 7.2 million tons annually. The Soviet Union 3.1 million tons annually. And those were baseline figures, not including military allocations or strategic reserves. The oil production figures were perhaps the most illuminating. The United States 4.6 million barrels daily. The Soviet Union 0.35 million barrels daily. Ratio 13.1.1 in American favor. "Why are we requesting oil production figures for aircraft engine analysis?" Volkov asked. "Because oil is the limiting factor for engine performance," Petrovich said. "The Americans are designing engines with higher compression ratios and higher fuel consumption rates. They can do this because oil is functionally unlimited to them. We design engines with lower compression ratios because oil is rationed. That's not a design choice. That's a production availability choice." He pulled together the cumulative picture. The United States was producing 4,680 fighters per month, 1,240 bombers per month, 8,900 engines per month, 143,000 tons aluminum per month, production of 17 major aircraft types simultaneously, complete replacement of battle losses, plus reserve stockpiling, plus lend-lease support to Britain and Soviet Union. They're producing enough engines to replace every aircraft in their inventory 3.2 times per year, Petrovich calculated aloud, purely from monthly production. That's not war production, that's industrial automation. He gathered every intelligence report on American factory specifications. The Willow Run Ford factory, 8,185 square feet of production space, employing 42,000 workers, producing one complete B-24 bomber every 63 minutes. The Douglas Santa Monica facility, 2.2 million square feet, 10,000 workers. The North American Inglewood factory, 1.8 million square feet, 30,000 workers, dedicated P-51 production at peak rates, reaching 364 aircraft per month. Lockheed Burbank, 1.9 million square feet, producing 14 aircraft per day. 364 P-51s per month from a single factory, Petrovich said. That's 12 complete aircraft per day from one location. Multiply that across all American fighter production facilities. He started calculating. North American alone, 364 per month. Republic aircraft, 340 per month. P-47 production. Vought, 280 per month. Corsair production. Curtiss, 150 per month. Consolidated, 180 per month. Smaller manufacturers accounting for additional volume. Total American fighter production, approximately 4,680 per month, just as the intelligence report stated. Every figure verified through cross-reference. That's not an estimate, Petrovich said, setting down the calculations. That's verified capacity. They are manufacturing this many aircraft every single month, not in good months, every month. He moved to projected production through the end of the war. Based on current capacity and reasonable assumptions about expansion, the Americans would produce approximately 215,000 complete fighter aircraft between the start of 1944 and the end of 1945. Add bombers, transport aircraft and other military production, and the cumulative total of military aircraft reached 380,000 units. In 24 months, they will manufacture 380,000 military aircraft, Petrovich said. Soviet production for the same period, at full capacity, would be 52,800 aircraft. Ratio 7.2.1. Volkov was silent. This is not a technical competition, Petrovich continued. We can match their design sophistication. We can reverse engineer their systems. But we cannot match their production capacity. We do not have the industrial base. We do not have the raw material availability. We do not have the electrical power or the machine tools or the skilled workers. He pulled together one final figure, the economic analysis that encompassed everything else. The gross domestic product of the United States in 1944 was $210 billion. The Soviet Union's was $42 billion. American wartime spending was consuming approximately 43% of GDP for military production. Soviet military spending was consuming approximately 61% of GDP. They're spending 4 times more in absolute terms, Petrovich said, while spending a lower percentage of their economy. Their economy has grown while they've increased military spending. Our economy is shrinking while military spending consumes everything. The conclusion was mathematical, not subject to interpretation, propaganda, or ideological revision. The American advantage is not in engineering, Petrovich said finally. It's in the ability to sustain that engineering through industrial capacity. Every P-51 Mustang is not just a superior aircraft. It's proof of a production system that can sustain thousands of superior aircraft, and we cannot. By June 1944, Petrovich's predictions began manifesting in operational reports. The first validation: Soviet fighter squadrons in the Southern Theater reported encountering American P-51 Mustangs in increasing numbers. The aircraft were appearing in formations, not as individuals or pairs, but in organized squadrons of 12 to 16 aircraft. The tactical advantage was immediate and measurable. Soviet pilots reported that Mustangs exhibited superior climb rate at altitude, better sustained turning performance, and exceptional endurance. More significantly, when Soviet pilots achieved kills against Mustangs, replacement aircraft appeared within days. The attrition rate for Soviet pilot training could not sustain replacement cycles matching American replacement rates. By August 1944, Soviet Air Force casualty rates had increased 34% compared to August 1943. The difference was attributed in official reports to increased enemy activity. The deeper analysis, that American production capacity was now supporting higher operational tempos, was not discussed. By October 1944, the trend was undeniable. American fighter production had reached 6,240 per month. North American alone achieved 486 P-51s in October. Soviet production remained at 2,200 per month. The ratio that Petrovich had calculated, 7.1 in American favor over the subsequent 24-month period, was tracking accurately. Additionally, every new American aircraft type captured for technical analysis revealed the same pattern. The Lockheed P-38 Lightning fighter exhibited superior manufacturing precision, redundant systems, and design for endurance. The Republic P-47 Thunderbolt possessed identical characteristics. The Vought Corsair similarly demonstrated American design philosophy, prioritizing pilot survivability and system redundancy over structural weight economy. In November 1944, a damaged North American P-51D was captured near Poltava. This aircraft represented the refined production variant. Petrovich conducted limited examination. The aircraft contained improvements confirming his technical predictions: modified supercharger system with 1.8 bar pressure at cruise, improved cooling efficiency, and manufacturing tolerances refined to 0.04 millimeters on critical dimensions, tighter than the March specimen. "They're improving the aircraft," Petrovich said to Volkov. "Not replacing them, improving them. They're iterating design through rapid prototyping and fast production modification. We design once, produce for years. They modify design, retool assembly lines, and implement improvements within months." By December 1944, the full scope of Petrovich's analysis was validated in ways that no official authority could dismiss. American air forces achieved de facto air superiority over Soviet territorial airspace. German aircraft were eliminated as competitors. Soviet fighters were increasingly unable to intercept American bombers operating in daylight raids throughout Soviet territory. The arithmetic of production had become the arithmetic of air superiority. Simultaneously, examinations of additional captured P-51s, P-47s, and Corsairs revealed that each new variant incorporated improvements. The aircraft that Petrovich had analyzed in March 1944 was not the current production standard by December 1944. American engineering was not static. It was evolutionary, supported by production volume that allowed continuous iteration. Soviet aircraft design remained static. The Lavochkin LA-5 produced in March was identical to the LA-5 produced in December. Modification required factory shutdown, retooling, engineering redesign, and restart. Procedures taking 4 to 6 months. American factories modified assembly lines while continuing production at reduced volume, then accelerated back to standard rates within weeks. "They have structural advantages we cannot overcome," Petrovich told Volkov during a January 1945 meeting. "It's not technology, it's not design sophistication, it's industrial capacity, economic resources, and organizational flexibility. Those are national advantages, not engineering advantages, and national advantages cannot be reversed by engineering analysis." Specifically, the cumulative evidence confirmed every major prediction from the March 1944 assessment. 1. American fighters possessed superior specifications across all performance parameters, confirmed through combat data. 2. This superiority was predicated on industrial capacity, not individual engineering brilliance, confirmed through captured aircraft examination, showing consistent precision manufacturing in production aircraft. 3. Soviet production capacity could not match American rates, confirmed through intelligence showing American production reached 6,240 plus fighters per month versus Soviet 2,200 per month. 4. American ability to sustain casualties through rapid replacement would eliminate Soviet numerical advantage, confirmed through casualty rates showing American losses replaced within 14 days versus Soviet replacements requiring 60-plus days. 5. American design philosophy emphasized system redundancy, survivability, and endurance, confirmed through multiple aircraft types showing identical design principles. 6. The conflict would shift decisively in American favor within 12 to 18 months of March 1944, confirmed as accurate by January 1945, with American air superiority now de facto across all contested territory. Every single prediction from the dismissed technical assessment had proven correct. After the war, when archives were declassified and historians had access to production statistics from both sides, Petrovich's March 1944 analysis was proven accurate in virtually every numerical detail. The official post-war assessment confirmed that American fighter production reached 45,680 aircraft between 1944 and 1945. Soviet production reached 12,200 in the same period, ratio 3.7:1 in favor of the Americans. Total American wartime aircraft production, all types, 304,124 aircraft. Total Soviet production, 58,260. Ratio, 5.2.1 in American favor. The production capacity analysis was validated. North American Aviation's Inglewood factory had produced 7,956 P-51 Mustangs, an average of 497 aircraft per month over 16 months of maximum production. The engine production specifications were confirmed. Packard produced 55,837 Rolls-Royce Merlin engines, V1650 variant, for American fighters and bombers. Each engine maintained the precision tolerances Petrovich had documented in March 1944, manufactured at scale with variants measured in fractions of millimeters. In 1946, Soviet interrogators captured Petrovich during the post-war security review. The interrogation specifically addressed the March 1944 assessment and its prediction of American air superiority. The interrogator, a NKVD major named Volkov, no relation to Petrovich's assistant, asked a direct question. Your assessment suggested inevitable American victory through industrial advantage. Why did you not recommend surrender in March 1944? Petrovich replied with careful precision, because technical assessment is not political authority. I was an engineer, not a statesman. My responsibility was analysis. The response to analysis is governmental. The interrogator was silent for a moment, then asked, was your assessment accurate? Yes, Petrovich said. The American production capacity was exactly as documented. The aircraft specifications were exactly as measured. The ratio of production advantage was exactly as calculated. The interrogator closed his notebook. The assessment was archived as defeatist propaganda. It was marked inappropriate for distribution to field commanders. Thousands of Soviet pilots died in air combat after March 1944, under the belief that Soviet Air Force maintained parity with American forces. This assessment, if distributed, might have prepared our commanders for reality. Petrovich was silent. You understand this represents failure of Soviet institutional judgment, the interrogator continued, not failure of your analysis. Your analysis was correct. Our institutions rejected correct analysis because it contradicted preferred narrative. That is institutional failure, not technical failure. Petrovich was not prosecuted. He was quietly reassigned to civilian aircraft development after 1946. The March 1944 assessment remained archived, eventually declassified in 1991 with the opening of Soviet archives. Historians confirmed that every major prediction had proven accurate. The document that was ignored in March 1944 became the template for post-war understanding of American industrial advantage during World War II. The historical record proved Petrovich right in every detail. If this kind of detailed technical history interests you, you'll love our other videos analyzing WWII's equipment and strategy. Check out the playlist in the description. And before we wrap up with the bigger lesson here, hit that like button if you appreciate this level of research and detail in history content. The story of Major Ivan Petrovich and his March 1944 analysis of the captured P-51 Mustang is on the surface a technical narrative about aircraft engineering. Beneath that surface lies something more profound, a case study in institutional denial, the collision between objective fact and ideological preference, and the consequences of rejecting uncomfortable truth. Petrovich's predicament was not unique to Soviet Union. The pattern repeats throughout military history. Competent technical professionals recognize approaching disadvantage through systematic analysis. They communicate this reality through proper channels. And institutions, unable to revise fundamental assumptions about their own capability, reject the analysis as pessimism, propaganda, or defeatism. In Germany, aircraft designers had warned Hitler in 1943 that American aircraft production capacity exceeded German capacity by ratios approaching 3.1. They recommended immediate strategic negotiation. The recommendation was characterized as defeat psychology. In Britain, intelligence analysts had warned in 1940 that German production capacity was lower than British estimates suggested. The analysis was rejected as underestimating the enemy. In America, military economists had warned in 1944 that Japanese oil production was insufficient to support continued war operation. Japan could be strangled through economic pressure alone. The recommendation was ignored in favor of conventional military strategy. The mechanism of institutional denial follows a consistent pattern. Authorities create assumptions about capability, resource availability, and relative advantage. These assumptions become organizational doctrine. Technical professionals examine evidence and find the evidence contradicts doctrine. When this contradiction is reported, the system has three options: revise doctrine, claim the evidence is false, or dismiss the technical professional as defeatist. Most institutions choose the third option. Dismissing the messenger is simpler than revising doctrine. The consequence is predictable. The technical disadvantage identified by competent analysis becomes, through organizational denial, a strategic disadvantage. Petrovich saw this in 1944. By 1945, the Soviet Air Force was operating under air superiority disadvantage that could have been partially mitigated through doctrinal revision and tactical reorganization in 1944. That mitigation did not occur because Petrovich's accurate assessment was categorized as inappropriate pessimism. The broader lesson transcends WWII specificity. When technical professionals, operating systematically and conservatively, identify objective disadvantage supported by measurable evidence, institutional response should be analysis and doctrine revision, not dismissal. The cost of being wrong about technical assessment is institutional failure. The cost of being right and being dismissed is strategic defeat. Petrovich lived to see his analysis validated. Most technical professionals making similar warnings in similar circumstances do not live to see vindication. But whether validated or vindicated is less important than recognizing the fundamental principle. Technical analysis conducted by competent professionals examining physical evidence has a responsibility to accuracy that supersedes organizational preference for more optimistic narratives. The P-51 Mustang was not a superior aircraft because American engineers were more talented than Soviet engineers. It was superior because American industrial capacity enabled precision manufacturing, redundant systems, and design philosophy focused on endurance and survivability. Technical professionals recognized this. Institutions rejected the recognition. War outcomes reflected institutional failure, not technical failure. That remains the enduring lesson of Petrovich's captured aircraft examination in March 1944. Thank you so much for watching this technical deep dive into one of WWII's most revealing moments. We've explored how one engineer's rigorous analysis of captured American technology painted an undeniable picture of industrial disparity, a picture institutional authority wasn't prepared to accept. If you're passionate about military history, engineering, and the untold stories of technical professionals who saw what others couldn't, then subscribe to the channel for new uploads every single week. I also recommend checking out the related video appearing on your screen right now. It explores another case of WWII predictions that changed military history. See you in the next one.